Good morning, class. We are looking at statistics practice test number 2, module 2, chapters 4 and 5. Here's chapter 5, discrete probability distribution. So we are looking at discrete probability distributions. Does the table describe probability distribution? What is the random variable? What are its possible values? And are its values numerical? So this represents the number of gears in 3 bits. X is the number of gears 0, 1, 2, 3. And the probability for each case is given. The variable X, which is the number of gears in 3 bits, 0, 1, 2, 3, those are the variables, is a numerical random variable. And its values describe probabilities. Summation of P of X. So that's one criterion. Summation of the probability. We should add the second column to see if we get 1. When we add up 0.125, 0.375, 0.375, and 0.125, we do get 1. And is each value between 0 and 1? Yes. Each value is between 0 and 1. So therefore, the answer is yes. Now, a couple of things I want to point out. Number one, each one must be between 0 and 1. If any of them is negative or beyond the two numbers, this is not representing a probability distribution. The sum must be 1. When you add them up, the only time that it may not, and it still represents a probability if this is extremely close to 1, because sometimes due to round-off error, it might happen that when we add them up, we get like 1.0000, many zeros and then 1, or maybe we get 0.999, many nines. That could happen due to round-off error. Otherwise, it shouldn't, and the sum must always be 1. Probability of each individual case must be between 0 and 1. In a game, you pay 60 cents to select a 4-digit number. If you win by selecting the correct 4-digit number, you collect $3,000. How many different selections are possible? Well, n is the number of digits, which is 10, because 0 to 9, that gives us 10 digits, 10 possible numbers. And we have to choose 4 of them. There is no restrictions. Therefore, 10 times 10 times 10 times 10, or simply 10 to the power of 4, or 10,000. There are 4 spots. Each spot has 10 possible outcomes. What is the probability of winning? Well, would be n of winning over n of s. There is one way to win, and there are a total of 10,000, so 1 out of 10,000. If you win, what is your net profit? Well, we paid 60 cents to buy that. So even if we win, that means $3,000 minus 60 cents. That's the net profit. Write the probability distribution for this net profit if you win. Well, numbers, net gain, probability. $3,000, there's only one way to win. The rest, 9,999, they won't win. And the total is 10,000. So you can say 10,000 minus 1 gives us this number. What is the net gain? For the winner, the net gain is this number that we calculated. For everybody else is negative 0.6. And that's extremely important to pay attention to. That's the negative sign, okay? Everybody loses 60 cents. That's the bottom line. What is the probability of winning 1 out of 10,000? What is the probability of losing 9,999 out of 10,000? So very clearly, the number in this column over that will do the job. I hope everybody is comfortable with that. Clear? Questions? All right, same question. Find the expected value and do the interpretation. Well, first and foremost, this is from the previous page. Secondly, I'm going to remind you of some of the formulas coming up. Mu is the summation of x p of x. This is the mean, or you can call it the average, or the expected value, also known as expected value. Sigma squared is summation of x squared times p of x minus mu squared, or x minus mu quantity squared times p of x, and we do the summation on that. So let's make up a couple of columns. The first one, x times p of x. So this is our x column, and this is our p of x column. So this means multiply these two numbers and multiply these two numbers. When we multiply these two, we get 0.29994. When we multiply these two, we get negative 0.59994. Now, mu or summation of x px, add these two, gives us negative 0.3. The importance of that later on, we'll look at it, which is the interpretation of that. Now, since we want to find this is the variance when you take a root becomes the standard deviation. So to do that, we need x squared times p of x to use in this formula and grab sigma squared and then take a root. So x squared p of x, that means raise this to the second power and multiply it by this number. Raise this to the second power and multiply it by this number. When, first of all, the mu, find the expected value, we found it is negative 0.3. That's the expected value. Now this part, raise this to the second power times this, raise this to the power of second times this, and those are the numbers we get, okay? This number to the second power times 0.0001 is this. To the second power times this is this. And you add them up, becomes 900. Sigma is the same thing under the radical, square root of that. We have this part as 900 minus mu, negative 0.3 quantity squared. So just plug in this one and this one. Okay, everybody? Again, it's pretty straightforward. I hope everybody is following that. And so when you do the math, you end up with 29.9985, almost 30 bucks, everybody. Now, what does it mean? This is the thing that we want to pay attention to. So on average, a player, that means any player, that means all players. On average, a player loses 0.3, this expected value because it's negative. If it were positive, that would be a gain. 0.3, that means 30 cents per ticket with standard deviation of, this one we really go with $30. When it comes to money, we go with 2 decimals, by the way. So 2 decimals gives you $30. So everybody is losing on the average. On the average, the house, the one who's selling the tickets, is collecting 30 cents per player. Could somebody read this question, please?
A pharmaceutical company receives large shipments of aspirin tablets. The acceptance sampling plan is to randomly select and test 24 tablets. The entire shipment is accepted if at most 2 tablets do not meet the required specifications. If a particular shipment of thousands of aspirin tablets actually has a 5% rate of defects, what is the probability that this whole shipment will be accepted?
Excellent. Anytime you deal with statistics, the questions are normally word problems. We need to read and reread to understand what is given. What we are dealing with is a BD, binomial distribution. If we claim we are dealing with BD or binomial distribution, we must give back 2 numbers, n, happen to be 24. P is called the probability of success. Doesn't necessarily mean something that is positive, but the terminology is P represents the probability of success. In this case, the probability of defect, which is 5% or 0.05. 0.05. That's the idea, and I hope everybody's comfortable with the concept. Okay. So with that being the case, probability of x is n factorial over x factorial times n minus x factorial, p to the power of x, q to the power of n minus x. Mu equals np, sigma equals square root of npq, where q is 1 minus p. Those are the information from the binomial distribution. So to move on with that, let me give you the synopsis of a binomial experiment. And PD stands for probability distribution properties. Number 1, we have n identical or fixed number of trials. Each repetition of the experiment is called a trial. Each has only 2 outcomes, 2 categories, or 2 outcomes. Good, bad, yes, no, defect, not defect, defective, not defective. Probability stays constant. So this probability stays constant with respect to every item, and they are independent trials. That's the concept that we want to be very careful of. Okay, everybody, that's the idea behind BD or binomial distribution. BD or binomial distribution. When that works, and we give 2 numbers, the n and the probability of success, we can write this formula. And by the way, this is CNX. This is combination of n. Choose x, as you all remember. So with that being the case, we are going to write this for this question. For this question, n, because we're going to write this formula. For this question, n is replaced with 24. For this question, p is 0.05. And for this question, q is 1 minus p, or 0.95. So we are going to replace everything here with the proper numbers. So 24 factorial over x factorial times 24 minus x factorial times p, 0.05 to the power of x, times q, 0.95 to the power of 24 minus x. So for the sake of argument, if I was interested in finding the probability of x equals, I don't know, 1, I would replace the x with 1 here. Okay, 2, I would replace it with 2. 5, I would replace it with 5, and so on. It can go all the way to n 24, but obviously no more than that. We are interested in at most 2. That means probability of x less than or equal to 2. That means probability of x equals 0 plus probability of x equals 1 plus the probability of x equals 2. That's the meaning of it. And we get to this answer. I'm going to show you how to get that. As long as you write this formula and you write this answer using a calculator, is fine. But the concept is this. You plug in 0, gives you a number. You plug in 1, gives you a different number. 2 gives you a different number. You add those 3, and the sum is 0.8841. You don't have to do this by hand as long as you have this formula. And this, you're telling your reader you know exactly what you're doing. And so the next step, if you want to use a calculator, you can. So here's how we do that. If you go with the TI calculator, for example, second vars binomial PDF, you enter NPX and enter. If you enter N and P, only gives all probabilities from 0 to N. And if you're using binomial, CDF gives the sum of the probabilities. Okay, so what are we going to use? We are going to go with binomial CDF because we want to go from a 0 to 2 and we want to add them up. This is going to give us the sum. Okay, and remember, when you put n, it goes all the way to n. N is what? 2, right? So you put 2. So CDF, binomial CDF, okay, 24, 0.5 and 2, okay, 0.05, okay, the probability of success. The answer it gives you, of course, it has a lot more decimals. And if you stop at 0, next to it is 5, you go up by 1, okay? So I hope everybody is clear on that. Very straightforward, everybody. As you can see, this number is the same as what we have. Of course, we truncated it accordingly. It is known that 70% of managers of all companies suffer from job-related stress. What is the probability that in a sample of 20 managers, exactly 8 suffer from job-related stress? Part A. And again, this is reminding you of how we use a TI calculator. So first and foremost, this is a binomial distribution. How do we know that? N is 20, and either you suffer from the job-related stress or you don't. A manager either is suffering from the job-related stress or not. There are 2 outcomes only with the probability of 0.7. Okay, probability of 0.7, everybody. All right. Now, if that is the case, we are going to use the binomial distribution with all these formulas that we can grab from the formula sheet, where P is 0.7, Q is 1 minus that, or 0.3, and we're going to put that into this formula. So probability of X is N or 20 factorial over X factorial minus over times 20 minus X factorial times P to the power of X, 0.7 to the power of X, times Q, 0.3 to the power of N or 20 minus X. So we write the formula in this fashion. What are we interested in? Probability of 8 or X equals. If we were to do it by hand, we would write 20 factorial over 12 factorial times 8 factorial, 0.7 to the power of 8, 0.3 to the power of 12. And we do the math, and we come up with the answer. If we were to do it with, and again, it's important to understand the process. It can be easily done by hand. It's not that big of a deal. It becomes difficult when you have a few of them to deal with. But one of them is very straightforward. And so with that being the case, you go with a binomial PDF here. Why PDF? There's only one. You're not dealing with CDF. You're not dealing with the cumulative. You're not adding them up. Just one of them. And when you plug in, you get this number. And you write it with a bunch of decimals. For example, if you want to stop at number 2, next to it is 8, goes up to 3. I hope it's clear to everybody. So pretty straightforward, everybody. We are going to continue with the same question, and now we're going to change it to at most 8. And it's the same question. Everything that we had from the previous page, we write it, including this formula that we had. Now, what is the meaning of at most 8? That means probability of x less than or equal to 8, which means you calculate the probability of x equals 0, x equals 1, x equals 2, all the way to 8, and you add them up. And this is where it becomes tedious, because if you want to plug in 0 and 1 and 2 all the way, and you want to calculate it, it becomes too much. That's really the main reason you use a calculator. For only 8 is not a big deal. So the meaning of it is add up those values. And now we are going to use the binomial CDF. We're going to use binomial CDF with n being 20, the number of times, probability of success is 0.7, x value is 8. When you paste it, it gives you this number. And again, if we stop here at 1, since next to it is 6, it goes up to 2. Again, depends on how many decimals. On a normal basis, you want to follow what they ask you. You want to follow and write a lot of decimals, everybody. But specifically pay attention to what is being asked. At least 9 suffer from job-related. So that means probability of x larger than or equal to 9. That means probability of x equals 9, 10, all the way to n. Whatever n is, n happened to be 20, but for the sake of argument, even if it's 200, you go all the way there. And the way to calculate this, you may recognize this is the same as saying 1 minus part b. 1 minus the probability of x is less than or equal to 8. Because this starts from 9 and goes to 20. This starts from 0 and goes to 8. So 1 minus that, those are the complementary events. Subtract this number from 1, and there you have it. Find the expected value. We are still working on the same question. We continue with the next part, asking for the expected value, and we recall that mu is NP. Again, it's a binomial distribution with all the information that we found in previous pages. E or mu is N times P. Multiply these two numbers and you get 14. What it means that among the 20 managers with a 70% chance of stress related from work, we expect 14 of them to be suffering from stress. Find the standard deviation. Sigma is square root of NPQ. So sigma squared is simply N times P times Q. So 20 times 0.7 times 0.3 is 4.2. And sigma is the square root of that. And we put 2.05. As far as the number of decimals, again, you really want to pay attention to what they ask you. Would it be unusual to claim that 7 managers from this sample suffer from job-related stress? I hope you remember the usual would be mu plus minus 2 sigma. So you multiply the sigma by 2, you add it to this number, and you subtract it from this number. So mu minus 2 sigma, that means 14 minus 2 times 2.05. And mu plus 2 sigma, that means 14 plus 2 times 2.05. And they result in 9.9 and 18.1. Is number 7 in between? If the answer is yes, it's usual, because the usual is from 9.9 to 18.1. Otherwise, it's unusual. And it's unusual because 7 is not an element of that. This notation without that is looking like an epsilon is an element. This means not an element. An element has this notation, and this means not an element of this in set theory. So it's not in between, therefore unusual. Find the probability of a couple having at least one girl among 3 children. Well, we are going to use probability of at least 1 equals 1 minus probability of none. I'm going to use that. We also know that the assumption is that the probability of G equals probability of B equals 1/2. Probability of having a boy and having a girl are the same. By the way, they may or may not be, okay? In fact, biologically, I think it's not. So having said that, 1 minus P of none means 1 minus P of a B to the third. And I want to emphasize that because they don't have to be the same. In fact, if you follow the biology, they are not exactly the same. But for the sake of argument, let's say the probability of B is 0.45 and probability of G is 0.55, then you put 0.45 here. In this case, 1 minus 1/2 to the power of 3, which is 1/8. 1 minus 1 over 8 is 7/8. This is 1 over 8, everybody. Maybe I write that. This is 1 over 8. Okay, the second method is using binomial distribution. N is 3. And the probability of success is 0.5. At least one girl. This one is the probability of girl. Let's say the probability of having a girl is 0.6. That's what you use, not 0.4. At least. So this is the probability of success. We are interested in, to know what is the probability of at least one girl. So this, whatever that one is, doesn't have to be 0.5. And I refer that because normally that's the assumption. It may not be. So probability of one girl is, let's say, 0.7. You use 0.7. All right. We want the probability of X larger than or equal to 1 because at least one, that means 1 is good, 2 is good, 3 is good. What is not good is 0. So you have two choices. You can add them up, or you say 1 minus probability of 0, the complementary event, which ultimately becomes the at least 1 in this case. And remember, P of X is n factorial over X factorial n minus X factorial, P to the power of X, Q to the power of n minus X. Now replace them, the n with 3, P and Q are both 0.5. And again, that's what I mean. Let's assume this is 0.6. Then you put 0.6 here, 0.4 here, okay? You want to be very careful with that, the way you use it. So we're going to calculate this one and subtract it from 1. So P of 0 is 3 factorial over 3 factorial times 0 factorial. This one to the power of 0, this one to the power of 3. And I hope you realize this is 1, this is 1.5 cubed, or 1 over 8, or 0.125 is the answer. So 1 minus that. Again, we should use P of B equals 1 minus P of G for P of O in case I've been mentioning that. And so the answer is obviously 0.875 or 78 as we had it again and again and again. That is the normal assumption. But if it's not, let's assume P of G is 0.6. Over here, you use 0.6. Over here, you use 0.4. Okay. This is extremely important. If we assume probability of a G is 0.6, that means a probability of P is 0.4. Those are the values that we have to use in case, okay? So I want you to be very careful when you do your calculation. If an alarm clock has a 0.9 probability of working on any given morning, what is the probability that it will not work? And by the way, that's really not a good probability. So as you know, probability of its complement is 1 minus probability of A. So probability of working is 0.9. Probability of not working with this line at top, line segment, it's called probability of A not or A complement. 1 minus that makes it 0.1 or 10%. So if there's a 90% chance it works, there's a 10% chance it won't. And that's what I mean, it's bad, okay? Now, here's the concept that is used in quality control. What is the probability that two such alarm clocks will not work? Now, this is the concept of redundancy. If you have a situation where, for example, an alarm clock is not doing a good job, what happens if you do use two of them? Probability of W sub 1, that means the first one, okay, working, and probability of the first one not working. Those are the symbols that we use. Probability that the intersection, probability of the first and second alarm not working. We assume independency, and it's the excuse me, it's the product. Notice there's a excuse me, there's a 10% chance one of them doesn't work, but both of them, there's only 1% chance. That's why this concept of redundancy is so important. So there's 1% probability that two such alarm clocks will not work. We're going to continue with this and go to part C. What is the probability of being awakened if you have two such alarm clocks? Meaning we are assuming that we wake up to the alarm. So we said probability of working is 0.9, not working is 1 minus that, and here's the probability of both of them failing, so 0.01. So method 1 is very simple. Probability of being awakened is 1 minus the probability of not being awakened, which means 1 minus probability of not working, both of them not working, 1 minus 0.01 or 0.9. That's very 0.99, very straightforward. Here's the second method, addition. You recall probability of A union B is probability of A plus probability of B minus the probability of A intersection B. So probability of W1 union W2 is probability of W1 plus probability of W2 minus probability of W1 intersection W2, which means we are going to use 0.9 here, 0.9 here minus. This one is 0.9 times 0.9 because we are talking about working. Working is 0.9. We are talking about this one, everybody. We get to the same answer, 1.8 minus 0.81. The third method is using the binomial distribution. N is 2. You have 2 alarm clocks. Probability of success is 0.9. And we use this formula, which means we're going to use N equals to P 0.9 Q 1 minus 0.9 or 0.1. And we want the probability of X larger than or equal to 1 because if one works is good, if both of them work is good, what is bad is P of 0. So we use the complementary event 1 minus P of 0. And if we use X equals 0 in this formula, as you know, this is 1. If you work it out, this is 1, this is 1, and this one 0.1 to the second power is 0.01, and we get to the same answer. 3 different methods. Could somebody read this question, please? Anybody? I appreciate that.
During an NFL season, there were 256 games played with 1,307 touchdowns scored.
Poisson distribution.
Thank you.
Sure.
What was the mean number of touchdowns scored in each game during the season? Round the answer to the nearest what is that, thousandth? Yeah.
Perfect. So first and foremost, what is a Poisson distribution? The probability of the event occurring X times over an interval. The interval can be time, distance, area, volume, or some similar unit, is given by P of X equals mu to the power of X, e to the power of minus mu over X factorial, where e is the base of natural log, 2.7182818 continues indefinitely. Mu is the mean number of occurrences of the event in the intervals. And the parameters of Poisson distribution are mu and sigma, where sigma is square root of mu. In some text, instead of mu, they use lambda. I'll go over that in a moment. The mean number of touchdowns in each game is mean, or mu equals total number of touchdowns, in this case 1,307, over the total number of games, in this case 256. And that gives us a number. And we want with 4 decimals, 1, 2, 3, 4. Next to 4 is 6, we take it up to 5. So on the average, there has been this many touchdowns per game. That's the meaning of it. The probability of X is defined as mu to the power of X times e to the power minus mu over X factorial for a Poisson distribution. What is mu? This number. Now, you don't have to replace the E with 2.71828. If you put it into a calculator, it does it for you, and the difference is it gives you with many, many more decimals, and it's more precise. So that's the general case. On January 10, 2010, the Green Bay Packers and Arizona Cardinals played a playoff game in which there were 13 touchdowns scored. What is the probability that a random game would have that many or more touchdowns? In other words, we want the probability of X larger than or equal to 13. And I want you to know, in this case, if you were to calculate this, you have to calculate probability of X equals 13, 14, 15, 16, and sky's the limit. Okay? It never stops. You go with the complementary event of 1 minus probability of X less than or equal to 12. So you calculate this, you subtract it from 1. Now, calculating this, again, means use this formula and plug in 0, 1, 2, 3. Needless to say, you don't have to do it by hand because it takes a long time if you want to do it by hand. So we're going to calculate this using a calculator, very similar to binomial distribution. So second variables, Poisson PDF, enter mu or lambda. This is what I mean, class. This is lambda. And in many texts, instead of mu, they're going to use lambda. So lambda to the power of x, e to the power of minus lambda. That's the notation, not a big deal. So we enter those values, enter or paste. If using Poisson CDF, it gives the sum of the probability from 0 to x. And in this case, we want from 0 to 12, right? So notice what we are going to do. Poisson CDF, lambda, rather than this number, I put the number with more decimals, class, because I want to, when you use a calculator, you want to get a better result. X value is 12. Since I just put the X value, it means calculate all the way from 0 to 12. And it gives me this answer. This is 1 minus that. 1 minus that. And if we stop with the 4 decimals, since after the 4th decimal, this is 0, this number remains unchanged. So it's about 0.0024. So the probability is pretty slim. If you were to go by percentage, would be 0.24%. 0.24%. That's how small it is. All right. We want to fill up this table. The first column lists the number of touchdowns, 0, 1, 2, 3, so forth, in a game. This is filled in already. The second column is for the predicted probability within 4 decimals that a game chosen at random will have that many touchdowns scored. Calculate these values, round them to the nearest 10,000s. The third column is for your best prediction about the number of games during the season that had that many touchdowns scored. Round them to the closest whole number. I'll tell you what's going on. Let's just do a couple of them and you see what's going on. First and foremost, I'm going to remind you about what we got in the previous page. And for example, if you look at 0, we want to calculate the probability here. You plug in x equal to 0. Just as an example. Again, you don't have to do it by hand, but if you were to do this by hand, for the 0, you replace the x with 0. And this is pretty straightforward. This is 1, just e to this power, that class. And if you plug it in, you get this number, 0.006. And it continues indefinitely. Now, if you go with the Poisson PDF and calculated class, so we did this. I'm showing you step by step how the answer. That Poisson PDF gives you the same answer. I want you to take a look at this one. Take a look at this one. They are the same. And you put it here. These two are the same class. Okay. This one, you put it here. That's what they're asking you. Now, How many games were there? $256 games. So what they mean here, whatever this number is times 256, okay? So basically you calculate this column and you multiply by 256. So when we multiply this number by 256 gives us this number. And again, I changed, I'd rather write with a lot of decimals, but I'm changing it to 4 because they said so, okay? Now look at this number. This is what you get, but the reason, and that's this one. The reason I change it to 2, because we are going to go with the whole number, everybody. And you do the same thing for number 1, so on and so forth. So now change this to number 1, calculate it here. Change this to number 2, guys. So I'm going to show you a couple more just for the sake of argument. For number 1, okay, and I don't have room to show you. And we put this number here, and then you multiply it by this, you get this one, you put it here and you round it. This one, 0.03009. Because next to it is 5, this changes to 10, so you put 0.310. I hope you see that. Look at this number. Is this one. Now multiply this one by 256. You get 7.92. And 7.92, we are going to write 8 because we want to go with the whole number. Let's do one more. Number 2. If we do number 2, class, the calculation results in this number, 0.0790. Next to it is 2, so we're going to keep it at 0. It's this number. And then we multiply it by 256, we get this number. And since we're rounding it to the whole number, it's just 20. And then you have to continue. As long as you can calculate a few of them, that means you know what to do. So you're in good shape.